Hello world, my name is Pedro DiConchi, and today I'm super excited to be talking to you about graphs. Hopefully by the end of this talk, you'll have learned something that has blown your mind in some sort of a way. So why am I talking about graphs? I think graphs are an absolutely fundamental data structure that are essential for computer science students to know and be aware of, because they have a variety of different applications to many interesting types of problems. For example, we can represent a map as a graph and derive information from the map through applying few different types of algorithms to the graph to get information such as the shortest path between 2 points in the graph, or even a path that contains the least amount of traffic between 2 points in a graph. They also commonly appear in technical interviews when you're trying to get a job, and they are just pure awesome. So the agenda for today's talk is going through commonly used graph terminology, the different types of implementations of a graph in memory, such as an adjacency list and an adjacency matrix, and two core essential graph traversal algorithms: breadth first search and depth first search, as well as their implementations in code. So some common graph terminology is a vertex, which just is a node in the graph, an edge, which connects two nodes together, a weight, which is a cost associated with an edge, and a directed edge, which is a type of edge that travels only in one direction, and an undirected edge, which travels in two directions. An analogy to all these different terms from before is that of a map. So if we apply all these terminologies to actual things from a map, a vertex would be a location in a map, an edge would be a road in a map, a weight would be a distance of a road in a map, a directed edge would be a path in the map that only travels in one direction, and an undirected edge would be a path in a map that travels in two directions, from source to destination and from destination to source. So these are two examples of visual representations of a graph. We have an undirected graph on the left-hand side and a directed graph on the right-hand side. So on the left-hand side, we have three nodes, A, B, and C. There is an edge between A and B, an edge between B and C, and an edge between A and C. We can travel from any node to any other node in this graph, since each edge travels in both directions. Whereas on the right-hand side, we have a directed graph with directed edges, and A can only travel to B, and C can only travel to A and B can't travel anywhere because there's no outgoing edge to any other node in the graph. Now I'm going to talk about two of the most commonly used graph data structure representations in memory: adjacency lists and adjacency matrices. I'm going to go over the pros and cons of both and when you'd want to use one over the other. Also, I'm going to use the graph shown below to model these two different memory representations. So in this graph, A has neighbors B and D, B has neighbors E and D, and C has neighbors A, D, and E. D and E have no neighbors because they have no outgoing edges to any other nodes in the graph. So the picture on the left is a visual representation of what an adjacency list looks like. It's a list of lists, meaning that it's a list of all the nodes in the graph, and each node in the graph is tied to another list which contains all its neighbors or nodes that are adjacent to it. It's best for sparse graphs or graphs that don't have any connections. It's memory efficient in that it only uses memory for nodes that exist in the graph and their connections. And one con is that for some operations, such as determining whether or not two nodes are adjacent to each other, it takes linear time instead of constant time, which we're going to see with an adjacency matrix. So this is an adjacency matrix as shown on the left. It's a 2D matrix representation of all the nodes in the graph. It's an n by n matrix, where n is the number of nodes in the graph. 0 signifies not neighbor, and 1 signifies neighbor. So in this case, looking at the first row, A to A doesn't have a connection, A to B does have a connection, A to C does not have a connection, A to D has a connection, and A to E does not have a connection. So we follow this going down, and we can see B and D has a connection, and B and E does, C and A does, C and D does, C and E has a connection, and there are no other connections going down the graph. Adjacency matrices are best used for dense graphs or graphs with a lot of different connections between the nodes. It's not memory efficient in this case because, as you can see, we have a relatively low number of connections and we're wasting a lot of memory. All the zeros in this graph or adjacency matrix are wasted space because they don't really tell us anything. And it sacrifices space for performance in many cases. However, it does have operations that are quicker than when we use an adjacency list. For example, determining whether or not two nodes are adjacent to each other is constant time complexity. Now I'm going to go over the two key essential graph traversal algorithms: depth first search and breadth first search. So DFS uses a stack to traverse the graph by reaching the deepest possible level first. Its time complexity is big O of V plus E, where V represents the number of vertexes and E represents the number of edges. Breadth first search, on the other hand, uses a queue to traverse the graph level by level. The time complexity is the same as a DFS with big O of V plus E for an adjacency list and a big O of V squared for an adjacency matrix. All right, now I'm going to talk about the DFS traversal in detail. I'm going to manually walk through an example of performing a depth first traversal on this graph. So to perform the depth first traversal, we need two data structures, a stack and a set. The set is just going to tell us whether or not we've already visited a node in a graph. And the stack will be actually used for the traversal. So all we need to do now is pick a starting point. I'm going to pick A as the starting point. So the first thing we do is we check to see if A is in the visited set. In this case, it's not, so we just add it to both the visited set and the stack, and we print it out. Then we look at A's neighbors, B and C. B comes before C since it's in alphabetical order, so B is B in the visited set. Nope. Okay, so we add it to the visited set and the stack. And you print it out. Oops, that's supposed to be a B. Then we look at B's neighbors, C, E, and A. We've already visited A, so we can't go there. The next thing we haven't visited is C. So we add C to the visited set and the stack, and we print it out. Then we go to C. We've already visited A, we've already visited B, but we haven't visited D, so we add D to the visited set and the stack. Then we go to D, we've already visited C, but we haven't visited E, so we add E to the visited set and the stack. Then we go to E. We've already visited B and D, so we can't go anywhere here, so we pop it off the stack. We go to D. We've already visited C and E. We can't go anywhere. We pop it off the stack. The same with C. We've already visited A, B, and D. We pop it off the stack. B, we've already visited A, C, and E. We pop it off the stack. And A, we've already visited B and C, so we pop it off the stack. So our depth first traversal yielded the order A, B, C, D, and E. So enough of theory. I'm sure most of you are itching to see how DFS is implemented in code. So before we get started with coding up DFS, we have to actually represent our graph in some sort of data structure. So up here we have all the different nodes and their neighbors. So all we have to do now is put this into an adjacency list format. So let's do that. And as I'm coding this stuff, don't really worry about the syntax or the implementation of JavaScript code, but rather just try to understand the idea, the higher level idea. So we have A. A is tied to a list, and it has neighbors B and C inside that list. We have node B, and B has a list attached to it that contains its neighbors A, C, and E. C has neighbors A, B, and D. And D has neighbors C and E. And E has neighbors B and D. All right, so that's it. This is it. This is adjacency list data structure. So now, if you remember, there were two data structures we needed to write DFS. A stack and a set that tells us whether or not an element has been visited or not. So let's make that visited set. So this is just a set data structure. It's kind of like a hash table, except there's no key value pairs. There's just values. It tells you whether or not a value is in the data structure in constant time complexity. And for the stack, I'm just going to use the recursion stack. I'm not going to actually use a physical stack data structure that I implemented. And I'm going to recurse through the graph. And whenever I encounter a node I have not yet visited, I'm going to recurse further down a level in the graph. So this is how it's going to look. I'm going to write a helper function that will allow me to repeatedly recurse through the graph. So all we need is the vertex we're currently at in this function argument. So we're going to print out that vertex we're at currently. We're going to add it to the visited set because now we're visiting it. And then we're going to visit every single one of that vertex's neighbors. And if we have not visited it yet, we're going to recurse one level further down in the stack for the graph. So for every neighbor, if visited set has that neighbor, or it does not have that neighbor rather, we're going to recurse on that neighbor. So we're going to do helper vertex. And that's it. That's honestly all we have to do. I think we're done. There you go. That's the implementation of DFS. Super simple, super clean. And that will print out this expected output here, which I'm going to show you in a second. So now let's test this function, this DFS function. So if I go ahead and I run this code, it should give me this expected output, A, B, C, D, and E. Let's see if it does that. As you can see, it prints out A, B, C, D, and E like I wanted. So this method works perfectly. Now that I've gone over DFS in detail as well as its implementation, let's get into breadth first search. So the two data structures that are required to perform a BFS traversal on a graph are a queue and a set to determine which elements we've already visited, like DFS. So let's pick a starting point and go from there. So let me pick E this time, since you already picked A in the other example, and start from E. So the first thing we do is we add E to the queue and the visited set. And you print out E. Now we take out E, we look at all the members or neighbors adjacent to E, and we in-queue them. So in this case, it's B and D. And the only reason we're able to do that is because they're not in the visited set. So now the next element we look at is B. We take B out, we print it out, and we look at all the neighbors. We already visited E, but A and C are unvisited, so we add those to the queue. And the visited set. Then we look at D. We've already visited E and C, so we don't add anything to queue. Then we go to A. We've already visited B and C, so we don't do anything, and we go to the next element in the queue, C. We've already visited all the neighbors adjacent to C, A, B, and D, so we don't do anything. So we just print C out. And that is a BFS. So we have the order E, B, D, A, and C. Okay, now I'm going to perform the BFS on the same exact adjacency list in JavaScript code. So the algorithm requires two data structures, a queue and a set that contains all the elements we visited so far to prevent us from visiting elements that we've already visited. So let's make those two data structures. So queue and a visit set. And then the first thing we do is we add the starting point to both data structures. And then while the queue is not empty, we're going to perform the following algorithm. Because once the queue is empty, we've already visited every single node we can from the starting point. So while it's not empty, we're going to take out the first element from the front of the queue, and then we're going to cycle through all that element's neighbors. If the set does not have that neighbor, we're going to add it to both the queue and the visited set because we visited it at that point. And then we're done. We print out the node we're currently at, and that's the BFS traversal implementation on an adjacency list graph. As you can see, it's pretty simple, pretty clean. You can actually apply this and expand upon this algorithm to do a lot of more interesting things, but those things are beyond the scope of this talk. But feel free to search up a bunch of different graphing algorithms after listening to this talk. You'll see a lot of them use BFS within them. All right, so now I'm going to test to see whether or not my BFS implementation works. If you remember, on the previous slides, I walked through a manual algorithm of the BFS on the adjacency list. I started at the point E, and I got the output E, B, D, A, and C. And that's what I'm going to test in code. So I'm going to start at point E and traverse the same exact adjacency list, and that's the expected output I'm trying to get. So let's run this code and see what we get. So I got E, B, D, A, and C matches perfectly with expected output I got from manually walking through the algorithm. Looks like this method works perfectly. That's all I have for you guys today. Hopefully you learned something new about graphs, and now that you're well equipped to handle the basics of graphs, I encourage you to research further on the subject matter through Google or YouTube. There are a lot of interesting, complicated graph algorithms out there that I think are awesome. Make sure to follow me at Twitter at Pedram_Ticonchi. Thank you for listening, and thank you for viewing once again.